This is for section 9.2. 9.2, we continue with hypothesis testing for two samples. But what we're going to focus on here would be for small independent samples. So we'll continue with hypothesis testing for the difference between two means. But in this lesson, we're going to focus with small independent samples. For small independent samples, we're going to use t-test. We're going to use t-test. So before we go on to hypothesis testing for our t-test for two samples, I wanted to take you back to what we did with our previous lesson in 9.1. So 9.1, we worked on hypothesis testing for the difference between two means, and we focus on large samples. So for large samples, we use a z-test, and we're breaking it down to two cases for z-test here. The first case is when sigma 1 and sigma 2 are known. Regardless of the sample sizes, we use the z-test. The second case, when sigma 1 and sigma 2 are unknown, S1 and S2 are known, and the sample sizes are greater than 30, then we'll use the z-test. Today, we're going to focus on t-test. So I'm going to call this case would be the third case here, and let me highlight this. When sigma 1 and sigma 2 are unknown, S1 and S2 are known, and the sample sizes are less than 30. This would be case number 3, all right? So what's the difference between this one and case 2? Well, what we have here for case 3, N1 is less than 30, N2 is less than 30. That's why we're saying it for small independent samples. Versus in case 2, sorry about that, versus in case 2, what we have here, we have N1 greater than or equal to 30, N2 greater than or equal to 30. That is why it is for large samples. Okay. All right, so now we know what are the requirements for case 3 so that we can use the t-test. Then what we have here, the assumptions for the t-test for two independent means, these are very basic assumptions. The samples are random sample. The sample data are independent of one another. And when the sample sizes are less than 30, the populations must be normally or approximately normally distributed. All right, so here is what we have for our formula for t. Okay, so t equals to x1 bar minus x2 bar minus mu1 minus mu2. We know that there's no difference in the population mean, so the numerator, we only have x1 minus x1 bar minus x2 bar. And again, if mu1 minus mu2 is always guaranteed to be 0, why do we put it in our formula? We'll put it for theoretical interest that there's no difference in the population means, but it's not for computation. The denominator, we have s1 squared over n1. And notice again that we pointed out from our previous lesson, only the standard deviations are being squared, but not including the sample sizes. So S1 squared over N1 plus S2 squared over N2. So now, in terms of getting the critical value of values for z-test, for z-test, I provided for you with the summary. I provided for you with the summary page here for z, because it takes longer to read it from the normal distribution table. So therefore, for each test with the different alpha, we have the different critical values. So I provide this for you. For a t-test, I'm going to have you read from the t distribution table, just like how we did it in chapter 8. Okay. So now, for a t distribution table, I'm sure you recognize this table here. In chapter 7, we worked on confidence interval. In chapter 8 and 9, we worked on hypothesis testing. Okay. So here we have one tail alpha. If we have a left or right tail test, we would read it under one tail alpha. For a two tail test, we would read it on this one. Now, what I wanted to point it out here, the degree of freedom, as you already know that the degree of freedom are one less than the sample size. And I wanted to remind you that for right tail test, the critical value will be positive. So we're reading it from one tail alpha and our critical value will be positive. So let me write it down here. Right tail test, critical value equal to a positive value, which is directly from the table. For left tail test, our critical value will be negative of what we get from the table. So if you have a left tail test, you're going to read it under one tail alpha, and whatever the value from the table, you're going to do negative of it because left tail test has a negative critical value. Then for two tail test, the critical value is going to be both positive and negative. So you're reading it from the third row here for fructose alpha. Based on the alpha that's given in the problem, then you're going to go with respect to the degree of freedom. Then you're going to have both positive and negative. So now, the degree of freedom are one less than the sample size. Let's go back to our formula. On the bottom of our formula, it tells us the degree of freedom here. And let's try to understand this. Where the degrees of freedom are equal to the smaller of n1 minus 1 or n2 minus 1. What does this mean? Because we have two sample sizes, and that means we have two n values. We're going to use the smaller n value to find the degree of freedom. In chapter 8, we work on one sample. So we only have one sample size. We only have one n value. Then we just take n minus 1. But here, we expand it on to two samples, meaning that we have two sample sizes. We have two n values. How do we find our degree of freedom? It tells us here that the degrees of freedom are equal to the smaller of n1 minus 1 or n2 minus 1. So whichever n is smaller, you're going to use it to find the degree of freedom, okay? And we're going to box this formula. This is what we have here for our test value. And we're going to write a note that the degree of freedom is equal to n minus 1. And I'm going to say for two samples, use the smaller n value. That way you know, okay? So it's possible that in one example, you could be using n1 minus 1 to find the degree of freedom. In another example, where n2 is smaller, you could be using n2 minus 1 to find the degree of freedom. Now, what about when both n values have the same? So let's just say n equal to 20, n1 equal to 20, and 2 also equal to 20. Then it doesn't matter which n you use because it's the same value. Okay, so here in all three tests, we talked about it, that mu1 minus mu2 equals to 0. How we state our hypothesis is the same as how we did it in section 9.1. For a right tail test, we have x sub o, mu1 equal to mu2, x sub a or x sub 1, mu1 is greater than mu2. For left tail test, we have basically the same. The only thing we would change to would be we have it for the alternative hypothesis with the less than sign. And for two-tailed test, we would have the alternative hypothesis with the not equal sign. And what we notice here, in all three tests, the null hypothesis, x sub o mu1 equals to mu2. That's why in all three tests, mu1 minus mu2 equals to 0. Because if the mu1 equal to mu2, then if we take the difference of it, we will get 0. And let me write this one here, x sub 1, because Alex uses the notation of x sub 1 for the alternative hypothesis. All right, so now we have this table. We have this table. We're going to come back to this table to find the critical value. And remember what we said in chapter 8, for z-test, we do both traditional as well as p-value method. But for t-test, we only focus on traditional method. Okay, so let's take a look at what we have here in example 1. The average size of a farm in Indiana County, Pennsylvania is 191 acres. So here we have 191 acres in Indiana County. So this word average tells us we have the sample average. And we know that we're working on 2 samples. So therefore, this is the first set of data given, so I'm going to give it with subscript of 1. So F1 bar equals to 191. Anything belongs to Indiana County, we're going to give it with subscript of 1. Okay. The average size of a farm in Greene County, Pennsylvania is 199 acres. So this average here belongs to the second set of data. So it is the sample average, but we're going to call this F2 bar equals to 199. So that's what I analyzed here. Indiana County, X1 bar equals to 191. Greene County, X2 bar equals to 199. We have, what's next? Assume the data were obtained from 2 samples with standard deviations of 38 and 12 acres respectively. So here, we know it from 2 samples. So the word standard deviation, that tells us we have the sample standard deviation. Sample standard deviation. And what we have here, the first one where it tells us the word respectively, meaning that the first number belongs to the first set of data. So F1 equals to 38 and F2 equals to 12. Since I have both here, so I'll write standard deviations. So that's what we have here. And the sample sizes of 8 and 10 respectively. So sample sizes, this tells us N1 equals to 8 and N2 equals to 10. All right. Let me move this so that you see this part right here. All right, so N1 equals to 8 and N2 equals to 10. Can it be concluded at alpha equal to 0.05? Alpha equal to 0.05, that the average size of the farms in 2 counties is different. Is different meaning that's not the same, not the same meaning that's not equal. So this would tell us we have a Q-TEL test. All right. Assume the populations are normally distributed. Okay, so that's what we know from the problem. After we analyze the problem here, we have Indiana County, we have X1 bar, S1 and N1. Greene County, we have X2 bar, S2 and N2. Okay, so we need to decide whether we use z-test or t-test. So we're going to ask ourselves this question: is it z-test or is it t-test? Okay, we're going to ask ourselves this. We're going to see, I'm going to ask this question and we're going to see which one we're going to use. Based on the given information, okay, let's take a look at what we have in case 1 from section 9.1. Let's see if this applies. Sigma 1 and sigma 2 are known. We don't have that. We only have S1 and S2. And here it tells us that assume the data were obtained from 2 samples. That's why we know, again, we know the sample standard deviations, okay? So case one does not apply. Okay. Case two, sigma one and sigma two are unknown. That's true. S1 and S2 are known. That's true because we have S1 of 38, S2 of 12. N1 and N2 are greater than or equal to 30. We don't have this requirement satisfied because our N1 is only 8 and then N2 is 10. So meaning that case 2 does not satisfy for this problem because we don't have the N value satisfied. We're going to move on to case 3. So here's what we have for case 3. Sigma 1 and sigma 2 are unknown. That's true. S1 and S2 are known. That's true. Our sample sizes N1 less than 30 and N2 less than 30. That's true because N1 is only 8 and N2 is 10. So therefore, we decided that we're going to go by t-test. Okay, so that's the reason why. Okay, so we're going to say it satisfies the requirement for case 3. And I don't need to write down case 3 because we have it at the beginning of our lesson, which is sigma 1 and sigma 2 are unknown, S1 and S2 are known, and the sample sizes, and 1 is less than 30, and 2 is less than 30. That's the requirement for t-test. So we know that it's going to be a two-tailed test. So we stated our hypothesis. H of O mu1 equal to mu2. H of A or H of 1, mu1 is not equal to mu2. What's the claim? The claim that is different. So therefore, we put the claim right here. And it is a two-tailed test. So now, next we'll go on to find the critical values. For our two-tailed test here, we have N1 equal to 8 and N2 equal to 10. We're going to use N1 to find the degree of freedom. Okay, so the degree of freedom would be, for this problem, we would use N1 minus 1, which is 8 minus 1 equals to 7. We're going to read it with two-tailed test, and alpha for the problem is 0.05. Okay, let's see what we get from our t-distribution table. So we're going to go to two-tailed test with two-tailed test here, and alpha is 0.05 is this one here. We're going to map it down with the degree of freedom of 7. So two-tailed test with alpha equal to 0.05, and we're going to map it over with the degree of freedom of 7, and this will give us 2.365. So I went a little bit too far with my down arrow, but let me bring it over to you what we have here. So 2 tells alpha equal to 0.05 given in the problem. The degree of freedom equals to 7. This tells us the critical values of plus and minus 2.365. So because it's two-tailed test, we have the critical values are both positive and negative of the value from the table. Okay, so here we have our critical values of plus and minus 2.365. Let's highlight this, keep an eye on these values because we would need these values to draw our curve in step 4. So I'm gonna box this, okay? All right, we're going to compute our test value. Knowing what we have from our data summary here, P equals to x1 bar minus x2 bar, which is 191 minus 199. Mu1 minus mu2, this part is 0. So the numerator, this is what we have. The denominator, the square root of f1 square over n1, meaning that 38 square over 8. Plus x2 square over n2, meaning that 12 square over 10. The way we do our computation is exactly like how we did it in section 9.1. So let me share my calculator to go over the computation with you here. We're going to do 38 square over 8 plus 12 square over 10. So 38 square dividing it by 8, I'm going to press enter. Next, I'm going to do 12 square over 10. Okay, so 12 square dividing it by 10. That means I'm done with these two computations. I'm going to put a check off to it. Next, I'm going to add the result and take the square root. That will give me the denominator. So, well, sorry, this is supposed to be dividing it by 10. Let me redo this part. 12 squared dividing it by 10. Okay, we have 14.44. So we take the first result of 180.5, add it with the second result of 14.4, press enter. Then now we're taking the square root of the result here. This gives us 13.960 and so on. This is what we have here for the denominator. Please do not do any immediate rounding. Keep all the decimal places. So I'm done with everything in the denominator. The numerator, I'm going to do open parentheses, 191 minus 199, close it, and divide it by the answer from the denominator. So don't press enter. You can press enter to get the value here, but it's more convenient. So therefore, don't press enter. Just go on with your computation. Then this would give us negative 0.573 and so on, okay? Now, in general, Z, we know that we have to round exactly to 2 decimal places. For T, it could be 2 or it could be 3. So I'm going to round it to 2 decimal places here for this problem, but on Alex, it could be asking you for 3, okay? So we underline the second digit, which is a 7. We look at the digit to the right is less than 5. We'll keep the digit, the underlying digit as is. So this is our test value. Generally, that test value for Z, we're rounding it to 2, and for T, we're rounding it to 3. But it's not always 3. Okay. All right. So now we have our critical values, and this is our test value. So here in step 4, to make the decision, we draw a curve, we mark 0 in the middle. The two critical values we found from step 2 are plus and minus 2.365. The positive 2.365 will put it to the right of 0, and the negative 2.365 will put it to the left of 0. As you already know that the tail part is the rejection region, and in between we have the non-rejection region. Now, where does our test value of negative 0.57 landed on? So a common question is that, how do we know whether we reject or we do not reject the null hypothesis? We see where does our test value landed on here. So negative 0.57 is to the left of 0, but it doesn't pass the negative 2.365, meaning that it landed on the non-rejection region. Because it landed on the non-rejection region, therefore, we're going to do not reject the null hypothesis. All right, so that's how we make our decision. Then now, the last step is to summarize the results. To summarize the results, we go back to see whether our claim from step 1 is the first or the second hypothesis. So in step 1, we put the claim as x of 1 or x of a. Then we go by the summary box, which we have it. I stated in 9.1, I stated in chapter 8 when we have our 5 steps in hypothesis testing. But here's the box that we're going to use. Here's the table that we're going to use. We said, do not reject the null hypothesis. So we use the table where we see the claim is x of a or x of 1. We go to do not, and here's what we would have with our sentence structure. So by now, you know that because we have the word not in our decision in step 4, then in step 5, there is not enough evidence to the claim is x of a or x of 1. then we would use the language of support, okay? So there's not enough evidence to support the claim that the average size of the forests in the two counties is different, okay? And like I said, that the nice thing about it on Alex is that you don't have to write out, you don't have to type out the whole entire sentence here. You have to select from the drop-down menu whether there is or there is not. Sometimes it asks you to select the word support or reject, but most of the time for step 5, you only have one fill in the blank. All right. So this is our first problem on hypothesis testing for two samples using t-test. And of course, t-test we go by traditional method. And in this problem, we have our N1 is smaller than N2. That's why we use N1 to find the degree of freedom. Let's take a look at what we have in the next example. Example 2, a researcher suggests that male nurses earn more than female nurses. A survey of 16 male nurses and 20 female nurses report these data. All right, so we have the summary data given in this problem here. We don't have to analyze much. So male, given that X1 bar equals 23,800, S1 is 300, and 1 is 16. Female, X2 bar, 23,750, S2 is 250, and N2 is 20. So here's what we have for our data summary. Then, is there enough evidence to support the claim that male nurses earn more than female nurses? So here we have the keyword for more than. That tells us the claim would be the one that where we have the greater than sign. And this tells us we have a right tail test. Okay, so the test here we have is a right tail test, but we still need to determine whether it's a Z test or a T test and use alpha equal to 0.05. All right, so based on the given information, before we go on to do our hypothesis testing, we need to ask ourselves that are we doing Z or T? Okay, so based on the information here, let's see if we check off for case 1. Case 1 from 9.1 that sigma 1 and sigma 2 are known. We don't have that. Case 2, sigma 1 and sigma 2 are unknown. That's true. S1 and S2 are known. That's true because we have the standard deviations here. N1 and N2 are greater than 30. That's not true in this case because our N1 is only 16 and N2 is equal to 20. So we don't have case 2 satisfied. We're going to check to see if we have case 3 satisfied here. Okay. Sigma 1 and sigma 2 are known. Excuse me. Sigma 1 and sigma 2 are unknown. S1 and S2 are known. That's true. Sample sizes, N1 is less than 30. That's true. And N2 is less than 30. That's true. So now, of course, we are working on the lesson for a 9.2 for t-test. So of course, it will be a t-test where we don't have to check it every single time. But the reason why I wanted to check it every single time because it's when you do your quiz or when you take your final exams or whether so in terms of the assessment, it does not break it down for you what lesson is from. So you're going to have to go through the elimination process to decide which one is the right one. So that's why I'm showing it to you. But of course, like I said, in this lesson, we're guaranteed that we're going to do t-test. Okay. All right, so we decided that is a right tail test. We're ready to go on to our hypothesis testing here. X of O mu1 equal to mu2, X of A or X of 1, mu1 is greater than mu2. And because the claim that male nurses earn more than, so here we have the more than, that makes this second hypothesis, which is the alternative hypothesis, is a claim. it is a right tail test, which is a one tail test. Alex always asks you to identify whether it's a one or two tail test. Left or right tail test is considered as a one tail test. All right, we're now going to move on to find the critical value from our distribution table. What we noted here in this problem, N1 equal to 16, N2 equal to 20. It happened very similar to example 1 that N1 is smaller than N2, but that's not always the case, okay? So the degree of freedom here, we use N1 minus 1, which is 16 minus 1 equal to 15. Our critical value would be positive, so it will be directly from the table because we have a right tail test. So we're going to read it with the degree of freedom of 15 under one tail test, and our alpha given in the problem is 0.05. Let's verify this from our table. We're going to go to our P distribution table. This time, because it's a right tail test, we're going to done. We're going to read it from one tail alpha, the second row here, and alpha equals to 0.05. Okay, so 0.05, and we're going to go down to the degree of freedom of 15 right here. Okay. All right, I went a little too far this time again, but that's okay. I'll bring it closer for you to read it. So we have one tail test with alpha equal to 0.05, the degree of freedom of 15. This gives us the critical value of 1.753. Okay. And the critical value is positive for this problem. It's positive because it is a right tail test. All right. And here is what we have for our critical value. Again, keep an eye on this value because we would need this value to draw our curve in step 4 to make the decision. Okay, so we're ready to compute our test value here. Test value T equals to x1 bar minus x2 bar. X1 bar we have 23,800 minus x2 bar of 23,750. Mu1 minus mu2, this part is 0. The denominator, S1 squared, the square root of S squared, S1 squared over N1, so it's 300 squared over 16, plus S2 squared over N2, 250 over 20. Again, I'm going to share my calculator to go over the computation with you here. I'm going to do 300 squared divided by 16. All right, so first computation, 300 squared divided by 16, I have this. So I'm gonna go ahead, check off this. I'm done with this computation. Next, I'm going to do 250 squared divided by 20. So 250 squared, dividing it by 20. Here's what I have. I'm going to check off this. Next, I'm going to add them together. Okay, so I'm going to take the first result here, add it with the second result. Then we get the sum. We're going to take the square root, and this will be what we have in the denominator. So I know that many of you are really good with your calculator. You can key in the whole equation at once, that's great. But since I'm teaching, I prefer to break it down into smaller steps so it's easier for our students to follow through. Okay, next we're going to move on to the numerator. We're going to key in as verbatim as how we see it with open parentheses. So open parentheses, 23,800. When we key in, we don't key in with comma. Minus, we have 23,750. Close it, but don't press enter. You're going to go on to divide it by the result from the denominator and press enter here. So here we have our test value of 0.5345 and so on. in my guided notes here, I'm rounding it to 2 decimal places. Underline the second digit, which is a 3. We look at the digit to the right, it's less than 5 because we have a 4 here. So we keep the underlying digit 3 as is. And this would be our test value. Let's highlight this, okay? All right, so like I said again, that in my guided notes here, I'm rounding the test value to 2 decimal places for our test value. But on Alex, for t-test, it could be asking you for 3 decimal places. All right, so we're ready to make the decision. We draw our curve, we mark 0 in the middle. Our critical value from step 2, we found that 1.753, which is positive. We mark it to the right of 0. Then the tail is the rejection region. Anything to the left of it will be the non-rejection region. Now, where does our test value of 0.53 landed on our curve? Well, 0.53 is to the right of 0 because it's positive, but it doesn't pass the 1.753. So meaning that our test value t of 0.53 landed on the non-rejection region. Because of non-rejection region, meaning that do not reject the null hypothesis. We have the word not in our decision here. Then when we summarize it, we go to the table where the claim is X of A or X of 1, which we use the language of support. So there is not enough evidence to support the claim. The claim that, and what's the claim? The claim that the male nurses earn more than female nurses. Okay. So that's what we have for this problem. And what we have here, this is our second example for a t-test, the t-test for 2 samples, and we go by traditional method, and this problem is a right tail test. Okay, the first example, we did it for 2 tail tests. Here we have a right tail test. All right, I have one more example for you, one more problem for you here, and this will be the practice problem. Okay, so what we have for the practice problem here, tax-exempt problem properties. A tax collector wishes to see if the mean values of the tax-exempt properties are different for the 2 counties. Okay, so we know it's going to be a right tail test. Excuse me, different meaning 2 tail test. The values of the tax-exempt properties for the 2 random samples are shown. So we have CDA and CDB. We have raw data, okay? So as you already know, raw data, we would need to get the data summary, and I'll review on how to get the data summary in a minute. So the data are given in millions of dollars. As alpha equal to 0.05, we know alpha equal to 0.05. Is there enough evidence to support the tax collector's claim? And what's the claim? Let's highlight the claim. The claim that the means are different. And again, this would tell us because of the word different, we would have a 2 tail test. So different meaning that's not the same meaning that's not equal. So when we write up a hypothesis, we would put the claim where we have the not equal sign. And let me write it down. 2 tail test. Okay, so next we need to get the data summary. Everything belongs to CDA, the first set of data. We're going to give a subscript of 1. Anything belongs to CDB, we're going to give it with subscript of 2. Okay, so what we have here, we're going to key in on our calculator for CDA. I'm going to cover this. Okay, we go to stat, we go to edit, press enter. If we have an existing data, we're going to clear it out. So go up to L1, press clear, press enter. All right, now here it doesn't matter if you entered in by row or you enter in by column. as long as you enter in all the data values under the same list. Okay, so I'm going to do 113, 22, 14, 8. That's the first row. 25, 23, 23, 30. That's the second row. 44, 11, 19, 7. That's the third row. Last row, 31, 19, 5, and 2. The nice thing about this lesson is that because we work with small samples, okay, we're dealing with two samples, but the sample is small, meaning that even if we have raw data, our raw data will be guaranteed at less than 30. All right, so I'm gonna go ahead and do the computation here. You go to step, all right, you move it over to help. You're going to go down to 1 bar step. Now, if your calculator display in this format, then your list will be L1, your frequency list will be blank, and you press enter, okay? And here's what we have. We have X1 bar is 24.75. Whenever we have raw data, we're going to use the SX instead of sigma X. So SX is 25.965 with more decimal places, but we'll just do 3 here is good enough. Our N1 is 16, that's 16 data values. Let me show you what happened if you have a different format. Let me change it to this one here. Then when you do your computation, you're going to have just this, okay? It doesn't ask you for the frequency. It doesn't ask you for the list of the frequency list. So then you just press enter. You will get the same value. All right, so now the second set of data will be similarly, but I'm not going to go over because you just clear out your calculator and get the data summary for CDB. For CDB, everything would subscript of 2, okay? And what we notice here, N1 has 16 data values because CDA has 16 data values. Likewise, with CDB has 16 data values, so N2 would be 16. So when we find our degree of freedom for this problem, it doesn't matter. It doesn't matter if we say N1 minus 1 or we say N2 minus 1 because we get the same value anyways. Okay. All right. So now, if I were to give you this problem on the final exam, are you going to use D test or T test? You're going to ask yourself this before you go on to do your hypothesis testing. So based on the given information, every single problem, you're going to go to the cutoff list to see which formula would it apply to. Case 1, sigma 1 and sigma 2 are known. We don't have that because we have raw data for CDA, raw data for CDB, and each set of data represents a sample data. So we don't have population standard deviations, but we have sample standard deviations instead. Case 2, sigma 1 and sigma 2 are unknown. That's true. S1 and S2 are known. That's true. N1 is greater than or equal to 30. We don't have this because our N1 is only 16. As soon as we fail one of the requirements for N already, we don't need to check for the other N value. So we know that Z test does not apply to this problem, to this practice problem. But we're going to see if t-tests apply here, all right? Sigma 1 and sigma 2 are unknown, that's true. S1 and S2 are known, that's true. Each sample size is less than 30, that's correct. So meaning that we have all the requirements for the t-test. And for t-test, we don't need to decide whether it's traditional or p-value because if it's p-value, then it will be z-test because our class for t-test, we only focus on traditional method. And also for the method, traditional versus p-value, you don't really need to decide because if you don't have the method indicated on the problem, that automatically means traditional method. If you have p-value method indicated on the problem, then of course you go by p-value. Okay, So we're ready to go on to a hypothesis testing here. We have x sub O, mu1 equals to mu2, x sub A or x sub 1, mu1 is not equal to mu2. And where do we put the claim? The claim that the means are different. So we put the claim where we have the not equal sign, okay? It is a two-cell test, all right? So what we're going to do here, we're going to find the critical value next. But like I said earlier, it doesn't matter which n value you use. So here you can say that degree of freedom equal to n1 minus 1, or in this problem, you can say that the degree of freedom equal to n2 minus 1 is still giving you the degree of freedom of 15, okay? So it doesn't matter which one you use. And I'm going to highlight both here. When n values are different, then it does matter. You need to use the lower n value. But when n values are the same, then it doesn't matter. Okay, so we know that alpha given in the problem is 0.05. All right, alpha equal to 0.05. We're going to go to our table here to read it for two-cell test. All right. So let me turn it over to two-cell test. Okay. We're going to be reading it from our third row for two-tails alpha. Alpha equal to 0.05 right here. And we're going to map it down with our degree of freedom of 15. All right. And here's, let me bring it closer for you to read it. So we're reading under two-tails alpha with alpha equals to 0.05, the degree of freedom of 15, that gives us 2.131. Now, because it's a two-tail test, we know we expect to see two critical values. So our critical values will come out to be plus or minus 2.315, 2.31. All right, so let's highlight these values here because we're going to need them to draw our curve in step 4. Okay. Now we're going to compute our test value t. What is t equals to? T equals to x1 bar minus x2 bar. X1 is 24.575. We did the computation. We didn't do this data summary for the second set of data. But after you do the data summary, you will get x2 bar equals to 42.938. Mu1 minus mu2, this part is 0. The denominator, the square root of s1 square over n1, 25.965 square divided by n1 of 16, plus s2 square, 72.745 square divided by 16. Okay, and again, I'm going to share my calculator to go over the computation one more time, but I hope I don't bore you with the computation, but it's possible that I make mistakes, so I like to go over the computation to verify the result as well. Okay. All right. So, and this also our last problem for the lesson. So 25.96, 25.965, 25.965. We squared this divided by 16. This is what we have for our first computation. I'm going to check off this. Next is 72.745. 72.745 was squaring this divided by our n value of 16 as well. I'm going to check off this. Next, I'm going to add them together. I'm going to add the result together and take the square root. Okay, so go up to the first answer, add it with the second answer. Okay, that means I'm done with the addition. The advantage of it is putting a check off on what you are the computer here. It reminds you, not to forget the square root. A common mistake when I look at students' answer, I can tell whether they miss the square root or remember the square root. Okay. All right, so this is what we have for the denominator. 19.30, carry all the decimal places, all the digits. The numerator, we do open parentheses, 24.75 minus, we have x2 bar of 42.938, is that right? 938, that's right. Close the parentheses, divided by the result from the denominator. And this gives us negative 0.94189 and so on. Okay, for this one here, I round the test value to 3 decimal places. So underline the third digit, which is a 1. We look at the digit to the right is 5 or more because we have an 8 here. So therefore, we round our test value. We increase the underlying digit from 1 to 2. So we round it to negative 0.942. And let's help me to label. This is our test value. And we're going to highlight this value here. On your guided notes, you already have the curve draw out for you. On my notes here, my projection notes, I don't have it, so I'm going to go ahead and draw for you here. So what we have, we draw our curve, mark 0 in the middle, okay? One critical value we have is positive 2.131, which is to the right of 0. PV equal to 2.131. As you already know that the tail represents the rejection region. We're going to do another, the other tail here, which is the left tail. The critical value would be negative because we have both positive and negative, 2.131. Because it's negative, that's why we mark it to the left of 0. This tail here is also our rejection region. In between negative 2.131 and positive 2.131, we have the non-rejection region. So what we notice here, our curve divided up into 3 regions, but our test value can only land it on 1 out of the 3, okay? So our test value of negative 0.942, where does it land it on? Negative, so it's to the left of 0. But it doesn't pass the negative 2.134. So here it would be what we have for t equals to negative 0.942. T landed on the non-rejection region, meaning that when we make our decision, we're going to say, do not reject the null hypothesis. So this is our decision for step 4. And again, on Alex, the nice thing about this one is that you select whether reject or not reject, all right? So do not reject the null hypothesis. We have the word not in our decision. Our claim for the problem is x of 1 or x of a, so we're going to use the language of support. So there is not enough evidence to support the claim that the means are different. Okay. So this is our last problem for section 9.2. I give you 2 examples and 1 practice problem. And that's conclude our lesson for 9.2. And again, thank you for watching, and don't hesitate to reach out to me if you have any questions. You're welcome to join my live stream office hours, or you can ask me remotely. Thanks for watching again. Bye-bye. See you in the next lesson.